last day of our workshop. So it's my pleasure to introduce Jacob Tsimerman from Toronto. He will speak about O-minimality and Hodge Theory, Algebraicity of Hodge Loci, and Griffiths Conjecture.
Perfect. Thank you so much. It's a huge pleasure to be here. I want to sort of give this talk as, in a way, an introduction to O-minimality and specifically its applications to sort of algebraic geometry as kind of a maybe sort of a different way to view some basic results in Hodge theory, and then some new results as well through this new lens of sort of minimal geometry. So I want to introduce O-minimality, explain how it connects, and then give some applications, sort of reproving some new results and also giving some new ones. So let me start by sort of summarizing our motivation to some extent, though I'm sure this is well known to many people here. So ultimately, at least from my naive perspective, we want to study complex algebraic varieties. And we study them using their Hodge structure. Let's say if X is some smooth projective variety, you can look at its cohomology and you get this Hodge structure. And so the idea is that there's sort of a complex moduli space of Hodge structures, roughly of the form d mod gamma, which I'll specify a little bit more precisely later. And d mod gamma is not, usually at least, in most cases, it's not algebraic. But despite the fact that it's not algebraic, it contains a lot of maps from algebraic varieties. So given any smooth projective family, say, of course, you can go more general than that, let's say like x over y over here, you get a map from the base y, which is some algebraic variety, to your moduli space d mod gamma, just by sending every point to the Hodge structure of its fiber. And so the idea is you want to study d mod gamma in some way that's maybe not algebraic, but as close to algebraic as possible. So our goal, at least for the first part of the talk, before I explain the applications, is to equip d mod gamma with some kind of tame structure to mimic the algebraic properties you might want if d mod gamma were, say, a Shimura variety or something like that. So somehow d mod gamma is a complex manifold most of the time, or at least a complex variety, and we're trying to do a little bit better than that so that we have an easier time analyzing the algebraic data inside it. So to do that, let me begin by introducing the concept of structures. So this is the basis through which we talk about tame geometry in the sort of model theoretic sense. And most generally, let me see if I can, there we go. Most generally, a structure is just a collection S sub n indexed by the natural numbers, where each sub n is just a set of subsets of R to the n. So we're allowing, basically, we're specifying which subsets of R to the n are allowed in our structure. And we want some sort of basic conditions which reflect the sort of basic operations in first order logic. So first of all, we want it to be a Boolean algebra for every n. So we want each S sub n to be closed under finite intersections, unions, and complements. We want S to be closed under finite Cartesian products and coordinate projection. So if I have something in R squared that's allowed and something in R cubed that's allowed, and I take their Cartesian product, I should get something in R to the 5 that's also allowed. Likewise, if I have something that's okay in R cubed and I project it to R squared, I want that to be okay as well. And finally, this is something which is pretty basic as far as applications to algebraic geometry, although it's not strictly necessary in the formalism of structures in general. You want to allow sort of all polynomial operations. So given any real polynomial, because this is essentially a real theory, even though we're going to be applying it to complex analytic structures, you want to allow the zero set of all real polynomials in your structure. Okay, so this is our definition of a structure. Of course, as it stands, structures can be very large. In particular, the structure of all possible subsets of R to the n will clearly satisfy these conditions because it will satisfy whatever you want. Take a set, do whatever you want to it, you'll get another set. So we want to somehow restrict the set of structures to something which is more workable. And first, in just notation, in order to be able to talk about them comfortably, if you have a set which is in a structure, so a subset of R to the n that's contained in, say, S sub n, we say it's a definable subset of R to the n. Technically an S definable subset, but usually we'll leave the structure implicit because from context it'll be clear which one we're talking about. And likewise, if you get a map between two definable subsets, you say that this map is definable or S definable if its graph is. So just a notation to be able to talk about these structures. And it's not so hard to see that basic operations, topological operations, for example, like closures, interiors, and boundaries of definable sets are also definable. So just some like an explicit example here to give you a sense for how this works. If you have a definable set U and you want to talk about its closure, well, that's literally can be written in this form. It is the set of all points such that for every epsilon there exists some y such that this is true. And see, now if you form the variety of x, y, and epsilon where this is true, that's definable. You apply some projections and Boolean operations, and you get the closure of U. So likewise, you can do you can talk about the other basic operations in the same way. Okay, so let me first present a non-example of a structure. So the basic non-example is just the structure of real algebraic sets, constructible ones. So you throw in all zero sets of real polynomials. You take all intersections and complements. So you look at the Boolean algebra this generates. That's not a structure. And specifically, if you take a polynomial and you look at yet another variable, x naught squared equals p, and then you project, well, saying that x naught squared equals p is just the same as saying p is at least 0, because it's just saying p has a real square root. And so if you're going to allow real algebraic subvarieties inside your structure, which we always want to by definition, you have to allow inequalities as well, at the very least. So you are forced to include at the very least that much. And so here are some examples. In fact, here is the smallest possible example of a structure under a definition, even though it's not one that we'll work with very often because it's not big enough to accommodate the kind of functions we want. But here's the smallest possible example of a structure, is a structure of real semi-algebraic sets. So specifically, you allow not just zero sets of real polynomials, but inequalities. So sets where a specific real polynomial is non-negative. Look at the Boolean algebra generated by that. That turns out to be a structure. So that's the famous Tarski-Seidenberg theorem, which they formulate as a structure having quantifier elimination. But in fact, the content of this theorem is if you take a set that looks like this, and you project it to one dimension lower, you still get a set that looks like this. Right? So in our non-example, we saw that projections can give you more complicated sets. The content of the Tarski-Seidenberg theorem is this doesn't happen for this structure. Okay, and in fact, our definition, because we're throwing in all zero sets of polynomials, this sort of reasoning shows you that R-alg is the smallest possible structure. Okay, so now we're going to introduce this concept of ominimality, which will be some conditional structures to keep them sort of nice and easy to work with. And the definition is the following. It's very simple. A structure is ominimal if the one-dimensional sets that you can define are exactly as small as they could be, so it's the same as an R-alg. Specifically, the definable subsets of the real line are just finite unions of intervals, where we're using the word interval here in its most general sense. So we're allowing points to be intervals, we're allowing intervals to be open or closed or at either end, and we're allowing them to be infinite in either direction. Okay. Now it might seem a little strange the first time you see this because sort of we're only putting a restriction on the one-dimensional sets when all the fun stuff is happening in higher dimensions. But the point, of course, is that you're allowed projections in your structure. So somehow the idea is that if you had the ability to construct some very strange high-dimensional set, you'd be able to project it down to dimension 1 and get something very strange as well. That's not sort of clear, but that's the process through which controlling the one-dimensional sets will, in fact, control the higher dimensional sets as well. So that's what it means to be O minimal. So let me just convince you that being O.
We lost you.
Hello?
Can you repeat the last sentence? Would that
Oh, yes. I'm sorry.
No,
Just the last
it's not.
sentence? I was with you until the very end?
Yes.
After the definition, yeah.
Oh, sure. So,
Okay.
yeah, so this is what it means for a structure to be O minimal. So I was just saying, let me just convince you that being an O minimal structure has some payoff, that there's some reason you might want this. So suppose S is, oh, this is a very bad choice of notation. I don't know why I called this S. But S here is a definable set in an O minimal structure, whereas usually I call S a structure. So I apologize for that. But take S to be a definable set in an O minimal structure. Then it automatically has some nice properties. So first of all, S has finitely many connected components. Moreover, you have these nice stratifications. So for every positive integer k, you can stratify S into finitely many pieces, each of which is smooth to order k, differentiable to order k. And in fact, you can do better. You can give S something called the definable CK cell decomposition. So I'm not going to give a definition, but something a little bit nicer combinatorially speaking. And moreover, you have nice uniformity statements when it comes to definable sets in O minimal structures. So here's one that's particularly useful, and it's reminiscent of stuff you get in algebraic geometry. So if you have a definable family, by which again I just mean a map between two definable sets, and this map has finite fibers, meaning for every point of y, its preimage is finite, then you get some uniform bound on the fibers. So there exists some fixed number m, such that every point has fiber no larger than m. Okay. So somehow this is meant to convince you that O minimal structures are tame, and this kind of exemplifies the way in which they're tame. So first of all, they have fairly smooth decompositions, and some structures, you can sometimes upgrade this from like CK to C infinity and sometimes to analytic, though not always. And secondly, you get this kind of free uniformity statements of the form I'm presenting over here. Just a word of warning, some of your favorite functions are not definable. In fact, you have to, you can still work with them, but you have to be a little bit careful. So a good example is the sine function from the reals to the reals, which in fact can't be definable in any O minimal structure. And one way to see this is that if it were, then the inverse image of a point would have to be a definable set, but it can't be because the inverse image of 0 is just the integers scaled by pi, but it doesn't really matter. And we already know, sort of by definition, that to be an O minimal structure, every definable one-dimensional set has to be a finite union of intervals. So the moral here, which is very relevant in applications to Hodge theory and other applications to number theory and algebraic geometry, is that periodic functions by discrete groups are in general not allowed, or somehow, or they form a problem, just like in this case here. Okay. So here are some examples of O minimal structures. And the idea, remember, is to have a structure to work with which is big enough to accommodate Hodge theory for the purposes of this talk, but small enough that we can sort of work with it nicely. So in particular, we want an O minimal structure with a lot of functions in it. That's somehow what we're searching for. So our alge is an O minimal structure. And here are some other ones. So Wilke showed, and this is based on earlier works of Hovansky on exponential polynomials, that if you look at Rx, by which I just mean the structure generated by the graph of the real exponential. So literally speaking, you throw in the graph of y equals e to the x, and then you take all possible Boolean combinations and all possible projections. You iterate that till you get a structure. It's sort of not hard to show that there is a smaller structure containing some given sets. Then that's in fact O minimal. Okay, even though it's a more complicated structure than our alge, in the sense that quantifier elimination does not hold. right? So for our alg, we showed that if you add the inequality relation, you don't need projections. You can work one dimension at a time. You don't get anything extra by going from a higher dimension to a lower dimension. That's not true, at least in an obvious way, for our exp. Next, another important example of an O-minimal structure, this is due to work by Gabrielov and Vendries, is Rn, which is in some ways a much bigger structure, though it's much easier to prove this fact than it is the Rx fact, it turns out. Rn, there's a few different ways to say it. My personal favorite is Rn is generated by the graphs of all overconvergent functions. So you can't quite throw in all real analytic functions. Otherwise, you'd have the sine function. And we just saw that the sine function is not definable in any O-minimal structure. But the problem with throwing in analytic functions is that at their boundary of convergence, they can behave in very irregular ways. You can have essential singularities, things like that. You want to avoid that. And so what you do is you look at functions which converge on some disk, analytic functions that make sense on some disk, and you are allowed to look at their graph on any smaller disk. This is hence the term overconvergent over here. And as long as you do that, as long as you stay a little bit less than the full radius of convergent, this turns out to be tame enough that the whole thing ends up being O-minimal. So while the sine function is not definable in Rn, right? We know it can't be. You can still work with it because its restriction to any finite interval is, because its radius of convergence is infinity. And if you go to a finite interval, that's obviously smaller. So even though you can't work with sine, you can work with sort of sine restricted to the interval from 0 to 2 pi, which morally is the entire data of the sine function because it's periodic. So somehow you can still work with these functions. You just have to be careful to look at them on restricted domains. Another way to say what this structure is, and in fact, it's often called the structure of subanalytic functions. You can say that it's a structure of all subsets of R to the n, which are subanalytic in some sort of compact closure of R to the n. So you can look at like real projective space, for example. That's an equivalent definition. You have to be a little bit careful because usually subanalytic, as it's stated, is a local property. And it's definitely not enough to say, it's definitely not true that every set in R to the n, which is subanalytic point by point, is definable. You have to be careful about what happens at infinity. And so if you throw in some compactification, that sort of takes that into account. Okay, and finally, a result of Miller and Vendries is that if you smush these two structures together, so you throw in Rn and you throw in Rx, and you look at the structure they generate, which is much bigger than either of them separately, that's also O-minimal. So this is, in fact, the structure which is used in basically all applications I'm currently aware of to algebraic geometry. You sort of really want to be able to deal with analytic functions, at least on small balls. That's why you want Rn to be there. You want enough functions to sort of make this a robust theory. But then you also need to talk about some degenerations. It's not enough to just talk about overconvergent functions. And so you want to throw in the real exponential. I want to point out just a couple other things before moving on. Even though we'll work with R and X, it's sort of not hard to find bigger structures. For example, Speiziger proved that if you look at the Pfaffian closure of an O-minimal structure, it's also O-minimal. So this basically means you're allowed to solve Pfaffian differential equations, i.e. you're allowed to integrate functions and families. That's kind of a moral way to think about what's happening here. I also want to point out that this previous bullet point, that if you throw in Rn and Rx together, you get something O-minimal, is not free. There are examples out there of two O-minimal structures where if you combine them and look at what they generate, you get something which is not O-minimal. So this is, in fact, something which requires proof. Okay. Any questions thus far? All right. So that's our foray into O-minimal structures. Oh, right. I also have this note here. There are maximal O-minimal structures just by some silly argument with profound induction, but with ordinal induction, sorry, but there is no single largest one. Meaning the examples of two, which if you put together are no longer O minimal. Okay, so what I want to do next is I want to talk about how to apply O minimality to complex analysis and eventually algebraic geometry. So even though O minimality is a real theory, the complex numbers aren't so far from the reals. So whenever you want to talk about definable subsets of C to the n, you just identify C with R squared, and you talk about definable subsets of R to the 2n. So it's not hard to import O minimality into complex analysis. And then you have the following sort of landmark theorem by Peter Zill and Starchenko, who initiated the study of O minimality in complex analysis, which is the following. So if you have a subset of C to the n, which is analytic everywhere, and separately it's definable in an O minimal structure, then in fact, this subset is algebraic. It's cut out by polynomial equations. So it's called the definable Chow theorem because, of course, if you replace C to the n with projective space, this would just be Chow theorem on the nose. The obvious point here is that C to the n is not compact. And so we see something which turns up a lot actually in the subject, which is that O minimality can function as a substitute for compactness in algebraic geometry theorems. So if you sort of get rid of the condition that you're working in a compact in a proper variety, but you throw in definability in some O minimal structure, you can recover definable Chow. So just to explain how this might work, let me give a sort of baby case of this to explain how these two different properties of being analytic and being definable in some O minimal structure can combine. So here's a baby case. Take a function from the complex numbers to complex numbers, which is analytic and which is definable in some O minimal structure. Then this function is a polynomial. This obviously follows from definable Chow, but let me explain how I would prove this directly. And there are several proofs depending how much complex analysis you want to use. Here's a very simple one. Since f is definable, the inverse image of a point has to be finite for all points because it's some definable subset of C. It's also a discrete subset because f is analytic. And therefore, by O minimality, it has to have finitely many components, so it's got to be finite. And therefore, it follows that f does not have an essential singularity at infinity, because we know that functions that have essential singularities take almost every value infinitely often. And that proves the theorem, because f is now analytic and does not have an essential singularity at infinity, so it's got to be a polynomial. Okay, so this is obviously a baby case, much simpler than definable Chow, but it gives you a sense of how you might sort of leverage O minimality to prove something like that. And then there's various other analogs I don't want to talk about in detail, but analogs of complex analysis theorems, which hold true in an O minimal setting. So you have definable Remmert-Stein, image theorems, stuff like that. Okay, so before moving on, I just want to very briefly talk about definable manifolds, which are pretty much they function how you would expect, with one small but important caveat, which is that all coverings have to be finite in this theory, because we're essentially doing first order logic, whereas usually any kind of manifold you would want, you would allow an arbitrary atlas to give a definable manifold, specifically given a structure S of any kind that will only use O minimal ones. And the manifold M and S structure is a finite covering by open sets, such that each open set comes the homeomorphism to something definable, and the transition functions are definable. Okay, that'll be very important, the finiteness there. Otherwise, it behaves like one would expect. And you can define S structures on whatever you want, smooth, holomorphic, etc. Okay, so now let's give some applications to Hodge theory. So a Hodge structure for us will be sort of the classical thing. We'll only talk about polarized integral Hodge structures because that's the context in which we'll get nice definability results. So we're going to have a lattice, a quadratic form, a direct sum decomposition of its complexification, satisfying the usual properties. Just like in the algebraic geometry setup, it would be sort of more convenient for talking about families to work not with the direct sum decomposition into the Hodge components, but instead to keep track of the filtration on the complexification. Right. Okay, so given a smooth projective variety, I'm going to go through this part quickly because this is a Hodge theory, conference. So people, I assume, are a little bit more familiar with the stuff. But if you work with the primitive cohomology of a smooth projective variety with some polarization given by a 1-1 from omega, then the primitive cohomology carries a polarized Hodge structure where the polarization is given by integration against this form. The decomposition is given by the Locaux cohomology, and the positivity just follows from the fact that this form can be taken to be Kähler. Okay, so let's fix a lattice with a quadratic form on it, and let's fix the dimensions of the Hodge components. Then what is the structure of the moduli space? Well, you have sort of a compact dual object. Specifically, we have the isotropic flag variety, parameterizing all possible filtrations, so all possible flags, which are isotropic under your quadratic form in the appropriate way. And then inside there, you have some open subset, in fact, some semi-algebraic set that's pretty easy to describe, such that the relevant positivity conditions hold. And then if you look at the algebraic group given by the automorphisms of your polarized lattice, then the complex points of this group act on your flag variety. The real points act on this subset D. They preserve this D. And the moduli space of Hodge structures, at least in the complex analytic sense, is just given by the sort of arithmetic quotient where you take D and you mod out by the integer points of your group. So in the baby case of elliptic curves, this gives you the familiar setting of the upper half plane mod SO to Z. And your moduli space here is algebraic. This is the Shimura variety setting. You just get Y1. Okay, and so we want to apply this to period maps, like we talked about earlier. So given a smooth projective family over some base B, you get some map from B to this moduli space M. And right now, this map only exists in the complex analytic category. And part of the goal of what we're trying to do here is to upgrade this to be definable in some O-minimal structure. So phi is holomorphic, but work of many people. So classically Griffiths, but then also Robos, Toledo, and others, is that M never admits this algebraic structure. In fact, M almost never admits non-trivial meromorphic functions. And the relevant theorem in this context, due to joint work with Bruno Klingler and Ben Baker, is that on this moduli space M, in this algebraic, you can put a definable Rnx structure. So that part's not hard. Just putting a structure on a manifold in general is not hard. You kind of break it up into finitely many pieces that are understandable, and you just declare them to be definable. And as long as your transition functions aren't too bad, that gives you an Rnx structure. The trickier part is showing that you have a structure such that all of these period maps are themselves Rnx definable, right? So these period maps flow from algebraic varieties to your moduli space. Your algebraic varieties have natural R-alg structures even, because they're literally given by algebraic equations. M is going to be equipped with this Rnx structure, and the point is that for this fixed Rnx structure, all these period maps become definable. Right. Okay, and so before I describe a little bit about how to do this, let me explain some corollaries that flow immediately from this definability. So first, just a word of notation. If we have a polarized Hodge structure of some even weight, weight 2n, excuse me, we call a vector in our lattice Hodge, an integer vector Hodge, if it's integral, and when you look at the Hodge decomposition, it sits inside the middle piece. So obviously an interesting set of classes, because if you look in algebraic families, you have the Hodge conjecture, where these are supposed to be the Hodge classes coming from cycles. And then we have the theorem of Katanidli and Kaplan, which would be a consequence of the Hodge conjecture, but they proved it unconditionally, that if you do have a smooth projective family, and so I'll phrase it in the following way, though it's possible to give slightly stronger phrasings, they end up being essentially equivalent. Let B sub m in the base be the set of points such that if you look at the primitive cohomology and look at the Hodge structure of the fiber, then that contains a Hodge vector of some fixed norm m. Okay? Then this locus on the base is algebraic. So you can upgrade that looking at the total family and keeping track of the vector, or you can remove this m here and just look at all points where the fiber contains some Hodge vector, and then you would need a countable union of algebraic varieties. The nice thing about this phrasing is, on the one hand, it gives you a specific locus on the base, which is actually algebraic, instead of having to talk about connected components, irreducible components. On the other hand, you can sort of phrase it directly on the base without having to talk about any kind of total space. Okay, so let me explain how once you have the right setup, once you have the right structures in place, you can prove this theorem pretty quickly. So here's how it works. So M is our moduli space of Hodge structures. Inside there, we have the locus M sub little m, consisting of all Hodge structures, abstract Hodge structures, which contain a Hodge vector of norm m. So that's a property you can define under an abstract Hodge structure. So that's some locus. It's easy to see that M sub little m is holomorphic. That's sort of an elementary fact. We'll see that for our RNX structure on M, in fact, this locus is definable. So once we see that, we have a definable holomorphic subset of M. Now, if M itself were algebraic, we could apply definable chow directly on M and conclude that M sub little m is also algebraic. So for example, if M were a Shimura variety, in fact, M sub little m would be a Shimura subvariety. It's not algebraic, so we can't do that. Nonetheless, once we pull back this locus to our base B under our period map, now we have a definable holomorphic subset of an algebraic variety B, and therefore the subset is algebraic by definable chow. So the idea is, even though you can't work with algebraic subvarieties because you're not in an algebraic variety, you sort of settle for talking about definable holomorphic subsets. And then the moment you interact with some algebraic structure, you can upgrade definable and holomorphic to algebraic. That's somehow the yoga for how you work with these things. Okay. So now that we have that potential application, let me talk a little bit about how one goes about constructing a definable structure on M. So to do that, let me go up to a slightly more general setup. Suppose we have gamma a discrete group which acts definably on some definable space X, some X equivalent definable structure, and consider the quotient. Well, sorry. Now, I want to clarify something, which is that in other categories like algebraic geometry, if I would write something like this, what I would mean is the map from X cross gamma to X is definable. I obviously can't mean that here because there's no way to give an infinite discrete group a definable structure. Definable sets have to have finitely many connected components. So what I mean here when I say that gamma acts definably on X is merely an element by element statement. For every element of gamma, the map it induces on X is definable. That's all that I mean. So let Y be the quotient, and we're trying to equip Y with a definable structure, just like what happens in the Hodge setup. So the sort of natural way to do this is you go up to Y, you pick a definable fundamental domain. So by which, again, I just mean a fundamental domain for gamma as a set, which itself is definable for the structure on X. And then what you can do is you can just say, well, Y is now in bijection with a definable fundamental domain F. So let's just import the definable structure from F onto Y. This is one way to give a definable structure on Y. Now, if you do this, you have the following nice characterization of the definable structure on Y in terms of maps to it from other definable sets. So in some sense, it's a definable functor of points. So given a definable Z and a map from Z to Y, let phi tilde be a lift of this map to X. Now, these lifts might not actually exist. I'll get back to that in a second. If this lift were to exist, then your original map is definable if and only if the following two conditions hold. The first is that your lift is definable, and the second is that your lift lies in finitely many translates of your fundamental domain. Right, so we see that the first condition here is independent of which fundamental domain we picked. That's just some lift into X. But the second one very much depends on our choice of fundamental domains. So let me talk briefly about the subtlety where, given the map from Z to Y, there of course does not have to be a continuous lift from Z to X because of monodromy and such. So what do we mean here? Well, because definable sets are sort of a cut and paste theory, it's a first order logic theory. All I mean is let's break up Z into finitely many simply connected pieces and lift each one of those into X. So if you're mapping from like a circle, because definability is not a continuous theory, but just a first order logic theory, you can break up your circle into a point and an interval, lift the point, lift the interval, and just separately ask that those two are definable. So when talking about definability, you have the advantage of being able to sort of make cut and paste arguments, so long as you only cut and paste into finitely many pieces. Right, so that's what we're talking about over here. So for example, if Z were the punctured disk, what you would do is you would just remove the positive real axis part of it. Then you get two things which are simply connected. You would lift each of those and ask for both of those to be definable. Okay, so alternatively, if you have a map from some Y prime, which itself was given by a quotient of a discrete group gamma acting on some definable space X prime, then you have a similar description where you want the map from X prime to X to be definable, and you want the image of a fundamental domain to lie in finitely many unions of fundamental domains in X. All right, so the moral here is that you can descend definable structures to quotients as long as you pick a definable fundamental domain. So here's an example to consider. Suppose we have the exponential map from C to C star. I've normalized it here such that the monodromy is actually the integers. And you can think of this as a quotient map. So you can identify C star here with C mod Z. And the usual fundamental domain that we all pick with, turns out we all are used to picking, turns out to be the best one. You take a vertical strip. This picture is due to Ben Baker. And you use that to be your definable fundamental set given your structure. To see that this is definable in R and X, let's remember that the real exponential is allowed in R and X sort of explicitly. And if we use real and imaginary coordinates, then what do we need? Well, we need the real exponential for the Y. We also need the cosine and sine functions, which we saw were not allowed, but we only need them on a restricted set, right? Because on a vertical strip, X is bounded between 0 and 2 pi. Cosine and sine restricted to that interval are definable in R and X. Therefore, this is a definable map. So an example of needing to be careful, which actually shows up more in the mixed case than in the pure case, though it shows up here as well, is that it is in fact sometimes unclear which definable fundamental set you want to pick, and it does in fact matter which one you pick. So if the obvious choices, one which look very natural, often give you the wrong structure. So here's an example. If you took the slanted strip, for example, in this case, and descended that definable structure, you will get a different definable structure in the complex numbers than the one we're all used to. So as an example here, you can look at the shaded region is definable inside C, and its image gives you this infinite spiral, which can't be definable in the usual structure because the intersection with the real axis has infinitely many components. And in fact, if you look at the definable structure here, then there are no definable analytic sets on this complex plane with its slanted definable structure. So you do have to be a little bit careful, and it's a bit of a subtle question, sort of in the most general setup, which definable structure is best. So which fundamental domain you should actually take to get the thing which is closest to being algebraic. That's something I don't have a general answer to. Okay, another example that's closer to the pure Hodge period domain setup is if you look at, say, gamma 2, to avoid sort of stacky points instead of gamma 1, and you look at the quotient from the upper half space to y2, then you look at the usual definable fundamental domain. And in that case, if you descend the definable structure induced by that, you get sort of the right thing. You get the thing which matches up with the algebraic structure on y2. To see that, you have to sort of be careful of the cusp is the only thing. Everything else is compact. You have to be careful of what goes on in the cusp. So in the cusp, you have something which looks like the j function at the variable q, which is e to the 2 pi I z. And the reason you end up with a structure in Rn x is that on a vertical strip, the j function is overconvergent, because it's actually convergent all the way up to the x-axis. So if you restrict to a bounded vertical strip, you get something overconvergent. You're plugging in e to the 2 pi I z, which again is fine as long as you restrict the x coordinate in some bounded range. And therefore, the inner thing is in Rn x, the outer thing is in Rn even, so the whole thing is in Rn x. Okay, so this is just giving examples of why you need the structure Rn x to accommodate these sort of Hodge theoretic functions that show up. Okay, so now with this sort of setup, we're ready to define the definable structure on the moduli space, on the period space. So let's recall our setup here. So what we need to do is specify a definable fundamental domain in order to descend our structure. And that's basically given by the theory of Siegel sets. So I'm not going to recall the whole theory here, but very briefly, given a parabolic subgroup, you have the Iwasawa decomposition, NAMK. That induces for you a theory of Siegel sets of quotients for GR mod GZ, basically, where you restrict the torus in some way corresponding to its positive root set. And the famous theorem is that if you look at finitely many of these Siegel sets, sort of one that's big enough for each conjugacy class of rational parabolics, then the union of these Siegel sets forms a fundamental domain for the integer points of your group acting on the real points of your group, as long as you're dealing with a semi-simple group. Okay, so there's some well-developed theory going back to Siegel and then the work of Borel and Harishchandra, using Siegel sets to form moduli for GR mod GZ, and then applying that to automorphic forms later on. And essentially, you can steal that when dealing with the quotient of D by GZ, because really D is just GR mod something compact. Things that are compacts are harmless. So you take the theory of Siegel sets and you can basically induce something on D, which works for our purposes. And if you restrict this to the case of Shimura varieties or the even more concrete case of elliptic curves, this exactly recovers for you the usual fundamental domains that we just had in the previous slide. So in fact, this gives you an RL structure on M. There's nothing going on here that's transcendental. Everything here is purely real algebraic. So you in fact get an RL structure on M. Sorry. Nonetheless, the period maps that we want to deal with will not be definable in RL, sort of far from it. They involve very transcendental functions. To get those to be definable, you have to include Rnx, like we've been talking about. Okay, and so now to tie this in with our application to the work of Catani, Dean, and Kaplan, if you now look at the sublocus that we defined earlier, m sub little m, of those Hodge structures admitting integral vectors of norm m, then they correspond to some orbit of some semi-simple subgroup h sub m, which you can construct by looking at the stabilizer of a primitive integral vector of norm m. And the theory of Siegel sets tell you that, in fact, finitely many Siegel sets in H sub m give you lie inside Siegel sets, finitely many Siegel sets in G, and that translates to saying that this is a definable subset, just like we want. So all of this is kind of is very sort of not easy, but classical, sort of well-known group theory for semi-simple groups. The hard part primarily lies in proving these period maps are definable. That's where all the hard analysis goes on. And we rely very heavily on work of Schmidt back when he was studying the one-dimensional setup. So let me recall how that works a little bit. So the important property which allows us to control these things analytically is Griffiths transversality here, where you insist that your directions send your pth piece filtration to at most one lower, the p minus first piece. And the fundamental lemma which sort of makes all this work is not even about algebraic varieties. It's really about maps from polydisks, which is the same as in the work of Schmidt and then follow-up work. They sort of understood that the fundamental setup is the case of a punctured polydisk. So suppose we have a Griffiths transverse period map from delta star to the m. And let's consider a lift of this map from the punctured disk to a vertical strip. Then the fundamental lemma, which makes all this work to show that period maps are definable, is that if you look at the image of this vertical strip to the power of m, the sort of the lift of this to the upper half plane, then that will lie in finitely many translets of our fundamental domain. So basically infinitely many translets of Siegel sets. And in fact, if you go to Schmidt's original paper, he has exactly the statement written down for the case of m equals 1. He exactly proved this for the case of dimension 1. And so what we have to do to prove this in general is to upgrade from the case of m equals 1 to the general case. And this is exactly the form that the proof takes. So instead of giving a more general proof, we take the case m equals 1 and show that that formally implies the general case. So let me just briefly spell out how that works. So it turns out that being in a Siegel set essentially amounts to some quadratic form being reduced, which shouldn't be that surprising if you're used to the theory of lattices, because the theory of Siegel sets really is motivated by the theory of quadratic form, and given a lattice finding a reduced basis for it. This was the original motivation of Borel and Harish-Chandra. And then if you translate that in our Hodge context, then that ends up amounting to showing certain inequalities of the following form, where H here is the Hodge quadratic form. You apply to some well-chosen integral basis EI and EJ, and you want to show that that's bounded above by the smaller Hodge norm. So this is sort of, you sort of take, if you translate back which form is reduced to the Hodge context, you get inequalities like this that you want to be satisfied. And now what we show is that these functions that we have to deal with are kind of controlled. So they're not quite analytic functions, but they behave in some sort of slightly larger ring, where you look at holomorphic functions on the entire disk, and you look at the polynomial ring over that, where you add these real functions, x, y, and y inverse. So basically, you have some rather well-behaved ring where all the functions you have to deal with lie. This relies on work of Kashiwara. And finally, we show that for any function of this form, to show that it's bounded above by 1, or which essentially amounts to showing that these inequalities up here hold, if you want to show that on the entire m-dimensional polydisk, it's actually enough to show it on the one-dimensional disks, and then it formally follows. right? So the point is that inside delta star to the m, you have lots of copies of delta star, basically given by all m-dimensional monomials. You look at all group theory embeddings of C star and C star to the m. You look at the image of delta star under that, and you look at translates. So you have sort of all these different copies of punctured one-dimensional polydiscs inside your punctured m-dimensional polydisc. For each one of those, Schmidt proved that this theorem is true. And so essentially, for each one of those disks, you know that whatever function you've concocted up here is bounded above on each one of those disks individually. And then we just show that these functions are such that if you know that, then in fact, you know a bound on the entire polydisk. So the proof really is taking the one-dimensional case and formally upgrading to the general case. Okay, so do I still have like a couple of minutes, or am I?
Yeah, 10 minutes.
Oh, I have 10 minutes. Okay, well, I probably need 10. But let me talk about another application then very briefly to Griffiths conjecture, using this kind of machinery. So we're in the same setup as before. We have a smooth projective family, and we obtain a period map from our base to our moduli space. Together with, sorry, Ben, I keep copying the wrong slide, so your name's always small instead of mine. That's the. Nonetheless, this is joint. This is joint work with Brunebar and Baker, which basically informally tells you that if you look at a period map and you look at the image of the base inside your moduli space, then you get something algebraic. So to make this formal, let me set it up in the following way. Let's assume, first of all, that your period map was proper to begin with. This is not a big deal this is not such a big assumption, because given any variation of Hodge structures, you can sort of extend to a log smooth setting where you will be proper. So this is kind of a minor assumption. And you can write down a statement in the general case, but it's a little bit less clean. So let's stick to this setup. Then you have a factorization of the map from your base Y to your moduli space M, given as follows. So you can factorize it as a dominant algebraic map from Y to Z, where Z is some quasi-projective variety, followed by a complex analytic closed immersion from Z into M. This is sort of the formal way of saying that the image of phi is algebraic. You sort of think of the image as this Z down here. Okay, so let me say a few words briefly about the proof. So first of all, the history of this conjecture was made by Griffiths, and he handled the case where the image of Y in M is itself compact. So in other words, your variation exists on an entire proper variety and doesn't generate anywhere. And in that case, he deduced the statement from the Corollary existence theorem. Basically, you can produce an ample bundle using Hodge theory, and that shows that you're a projective variety. So the hard part of doing this in general is dealing with generations and infinity. And then what we do is we essentially say, we use the definability to say, well, look, the image of Y inside M is some definable thing, which is also analytic. And then we show that given any setup like this, where you have an algebraic thing mapping to a definable analytic thing, the image is automatically algebraic. So essentially, the proof of this theorem forgets about everything to do with Hodge theory, only remembers that you have some definable structure on M for which this map phi is definable, and then says whenever that kind of setup holds, you get a theorem like this, where the image is algebraic. And essentially, the extra input in the proof, aside from what I explained here, our joint work with Klingler, that this is in fact definable, is the proof of the statement essentially follows some sort of deformation theory argument. So we have to upgrade the theory of definable complex analytic manifolds to some kind of theory allowing nilpotents. So essentially, we call them definable analytic spaces, where we allow structure rings that have nilpotents in them. And we prove sort of an O minimal GAGA for these statements, for these sort of creatures. And that's enough to prove this sort of statement. So let me end with a few remarks. So the intuition about this Griffiths conjecture in the end is that the analytic, you can think of it as sort of saying that the analytic property of having the same Hodge structure, which is a priori analytic, is actually, you can find an algebraic parameter space for it. One way to think about it is the following, that if you have this kind of period map from Y to M, you can form the relative fiber product inside Y cross Y, so sort of the relation of having the same Hodge structure. And that's easy to show that that's algebraic. Even though this is a priori analytic, the theorem of Katainen, Deline, and Kaplan essentially applies to this context and tells you that the subspace is in fact algebraic. And so what the theorem is showing you is that the quotient by this algebraic relation in fact exists. That's one way of showing this. Okay, so let me move on to the final slide here. I just want to mention some other work. So first of all, my student Abhishek Oswal this year proved a rigid p-adic Chow theorem. So in the rigid framework, there's no great analog of omnimality yet. People don't really understand. There's some partial work, but there's no sort of nice category like omnimality to sum up what a reasonable structure is. Nonetheless, you can restrict to the p-adic subanalytic setting. That's a setting that's been very well studied. And in that setting, you can establish, he established a subanalytic Chow theorem. You can prove analogous statements to the stuff here for mixed period domains. So this relies on work of Brosnan and Prostein and is itself due to joint work with Baker, Brunner, Barb, and Klingler, where you can show that they have definable structures, and you can also show that the images of period domains are themselves algebraic. And in the mixed setting, like I sort of mentioned a bit earlier, you have this slightly delicate issue of which definable fundamental domain to take, which is essentially solved by the work of Brosnan and Prostein. Actually, we basically look at their work and we copy what they do in order to get our definable structures. And finally, I think there was some work spoken on this at this conference, but you can use the definability results to prove transcendent statements between period integrals on algebraic basis. So there's sort of actionual statements, and there's some slightly some other work by Ben doing this. And that's all I had. So thank you very much.
Thank you. So are there any questions?
Yeah, I have a small question. Is that okay?
Sure.
Can you hear me?
Yes, I can hear you fine.
Okay, thank you. What is a guess about the field of definition of the map the moment it is algebraic?
Of the period map, you mean? Yeah.
So you give a variation. I think your notation was y2x or something, and then it gives you the map from x to your y. I'm sorry, y is the base.
Sure.
So y, and then everything is, I mean, not M is algebraic, but the target is algebraic, the map is algebraic. So there must be a field of definition should be defined in terms of I don't know, the absolute Hodge cycles or something, a field of the absolute Hodge cycles of the variation of the Hodge structure. I mean, what is a guess here?
Right, that's a good question. Of course, we can't prove anything, right? Because
we can prove something, no? So at least for the Stein factorization.
Oh, sure. Do you remember, Johan? Go ahead. You can answer the question if you remember what exactly the statement for the Stein.
Sorry.
No.
Yeah, no, but the thing, so if your variation is given by something algebraic, basically and you know that the filtration.
What does that mean by something which is algebraic? What does that mean?
So if you know that the vector bundle and the connection together with the Hodge filtration are defined over some subfield of C.
Or even just the Hodge filtration.
Yeah, even the Hodge, yeah, sorry. Even just the Hodge filtration, then at least the Stein factorization of this map is defined over this this field.
Can you say that again? Because I think Virginie closed something on my screen, so I had to pay attention to what she did. So I apologize.
No worries.
Can you repeat? Yeah, I'm sorry.
You have a variation of Hodge structure on Y.
Yes.
And if you know that the Hodge filtration is defined on a subfield of C,
yes,
then in fact, yeah, it is always the case. But if you fix this subfield, at least the Stein factorization of the map from Y to Z
is defined over this field.
Exactly.
Okay.
I want to point out, I mean, like Johan said, we can prove that that does fall. That's sort of a very immediate consequence of this theorem here, because basically what this amounts to is showing that if you look at the Hodge bundle on Y, or the Griffiths bundle, whatever you end up dealing with, then that has enough sections in some way. You look at certain types of sections and you sure it has enough sections. Now, once you know it has enough sections, those sections are obviously defined over whatever field the Griffiths bundle is defined over. And so,
or some finite extension of it, maybe, or what does that mean? Yeah, no, sections. I apologize. No, sure. Yeah, sure. Yeah,
just that same field. And then, so then you work out what that amounts to, and that amounts to the Stein statement that Johan is saying. Am I correct, Johan? I'm not messing this up, right? That's basically what happens?
No, I see. Yeah.
Right. So you have that statement. If you want to go beyond the Stein statement, then you need something like absolute Hodge, because you have to avoid the hypothetical where, say, Y is a curve, and maybe this map phi just identifies two random points of Y. Now, if you had absolute Hodge, you can say something about these 2 points have to have, an algebraic-ish field of definition. But if you don't have anything like that, then a priori those 2 points might be arbitrary, and then we can't say anything about the field of definition. So the Stein statement sort of follows from the fact that the Griffiths bundle, the bundle you want to work with, is defined over a reasonable field. And if you want to go beyond that, you need something like absolute Hodge.
Yeah.
Another way to state it is that the Hodge bundle, how do you say, it controls the deformation. So it will be trivial on the subvariety where nothing happens.
It controls the deformation, but only it doesn't see finite covers, so to speak.
No.
I understand. Yeah. Thank you very much. I have another small question in the same spirit. Is can you retrieve Deline's theorems that Hodge implies absolute Hodge for an abelian scheme?
Oh, I haven't thought about that.
No, it just occurs to me that one might try, using algebraicity to reprove Hodge. I mean, I don't know how to do it. It just occurs to me, but.
You're saying, can we reprove it for abelian schemes, or can we generalize it to other contexts?
Well, I mean, first I would.
Right.
I'm a very secular person, so I would try to reprove it and then.
No, sure. I was going to say no to the second thing, is my guess, without another idea at least. But
that I don't know. I mean, generalizing the link is always. We should not start with this question here. We should start with another one. But yeah.
I'm not sure. I haven't thought about it enough. I'll think about it and get back to you.
Okay. Now I mute myself because Virginie already made me invisible, and I mute.
Okay.
I didn't do anything.
Really? Because I'm no longer able, I mean, it doesn't matter, but I'm no longer able to start my video. It says unable to start video. The host has stopped it. This is what it says. But don't worry. I mean, Jacob should have questions. So I just.
So are there any other questions?
So can you hear me?
Yes.
Yes.
So in your argument using the Siegel domain, there's some finiteness arguments, which are sort of, you could say, are model theoretic, and there are some inequalities. To what extent can you state the property of the Siegel domains as a model theoretic additional condition on in your situation?
Sorry, I'm trying to understand. So you're saying in the context of period maps, or just in the context of like getting a fundamental domain for D mod gamma?
No, in the context of period maps, you used Siegel domains for period maps, and then
Yes. Right. I mean, one way to think about it, this was sort of explained to me by Schnell. One way to understand what Siegel domains do is sort of through the SL2 orbit theorem. If you had an actual SL2 orbit, then the Siegel domain becomes a natural thing, because you sort of, that's how you unwrap the disk, and that's also how you want to unwrap the image for them to match up. So if you look at like Y1, for example, and you ask for why we're using the Siegel domain there, well, that's just because there's a sort of in the quotient is the complex numbers. There's a unique definable structure there, like in the Shimura variety setting, which gives you sections.
yes.
And that tells you in the case of SL2 what to do. So the relevant property of Siegel domains that ends up being useful is that if you restrict them to every SL2, you get the right thing. That's sort of all we end up using.
Great.
Now, why it's exactly the Siegel domain that we use and not some other set, I can't really tell you. But that's the fundamental property of Siegel sets that ends up being used, is that on every SL2 you get the right thing. And why on every SL2 is this the right thing? Well, because there the quotient's actually algebraic, and so you want the unique definable structure, which sort of lets you realize that algebraicity. That's not a very satisfying answer. I do think it's the best answer I have at the moment, though, for why Siegel sets end up being the right thing.
Are you saying that any domain for which this SL2 property holds would work?
Yes, but I'm pretty sure you could prove that would just mean that it's definably the same as the Siegel domain. I haven't fully thought this through, but there's like in groups there's lots of SL2s with lots of conjugates, right? So so for a strong enough assumption like that, I think that would probably characterize your Siegel sets, though I haven't checked this formally.
Oh, cool.
Mm-hmm.
If I can just add something, and Jacob already mentioned this, but this is probably not true in the pure case, but in the mixed case, he said that there are sort of different omenable structures you can put in the period names. In fact, there could be different ones for which the theorem is still true, that period maps are definable. It's not clear.
Yeah. Ultimately, like historically, we use Siegel sets because we know about Siegel sets, and so they were natural things to try, and then the proof worked. It's much harder to go back in and say why does the right thing.
Are there any other questions? Okay, so if no, let's thank Jacob again.